Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Nikhil Sarin with us today. Hello, Nikhil.
Hello, Frank. How are you?
I am doing awesome on this October 29th of 2024 as we record this. And we are well past equinox. And so Phoenix is cooling down. We actually got cooled this morning. So that was very nice. And how about you? What's your geolocation?
I'm in Stockholm, in Sweden.
Uh-huh.
So as you can see, well past equinox because it's dark at 5 o'clock.
Yes, very definitely. But you do get some auroras up there. Have you seen the auroras?
Yeah. No, I've been fairly lucky in the last few weeks, especially, but then a
Yeah.
couple of years ago as well. Yeah, so
Yeah. That
been
one
really.
is still on my bit bucket to actually see in person. So
Oh, they're amazing. Yeah, they
maybe one day I'll
definitely.
do a trip up to Sweden or something like that. So it'll be very cool.
Yeah. You
Very
should you should probably do it.
yeah, yeah.
Much big weather change too.
Yeah. So what's your position there in Stockholm?
So I'm a postdoctoral fellow in Stockholm. Yeah, I'm currently in the Nordita building, which is a research institute.
Mhm.
So yeah, that's my
Yeah.
position.
Yeah, you have the appropriate squiggles on the blackboard behind you, so it totally looks like a research institute.
That's right. I've got my own whiteboard. So this is scribbles when I was trying to explain Gaussian processes to a student. So
Oh,
yeah.
very good. Cool,
Yeah.
cool. Let's see. And let's see. So, in general, then, what do you like to do for research, Nikhil?
So I like to work on basically what I would call the interface between gravitational wave astronomy and electromagnetic transients. So
Cool.
this field of multi-messenger astronomy that has been sort of blossoming since one of the discoveries
Yes.
that I'll talk about today. And really, I like to think about sort of the analytical modeling about the different phenomena that's going on and try to interpret what's the data is telling us about the transient phenomena and the neutron star merger themselves itself.
Cool. Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Cautionary tales on heating prescriptions in Kilonovae and Nikhil. Take us away.
Awesome. So yeah, this is a paper that we wrote recently with so me and Stefan Roswag. So Stefan Roswag is a fantastic co-author of mine, and he's a professor up in Hamburg University now. He actually used to be in Stockholm.
Mhm.
He's got a really nice office in the Hamburg Observatory. So it's a really nice, fun place.
Cool.
And he's someone who's been thinking about kilonovae since basically 1999, I would say.
Somewhere
So
around there.
since
Yeah. Yep.
before they were really popular, I would say.
Yes.
And then I came in when
Really
they were definitely
popular.
much more popular.
Very cool. Good shout
Um,
out. Good shout out.
yeah. So yeah, this what this paper is essentially about is, a cautionary tale on one of the main ingredients that goes on Kilonova itself. So I want to, before I sort of go into talking about this again, I just want to show a little movie to
Sure.
build the picture up about
Sure.
1717 and Kilonova in general.
Okay. And roll.
So a lot of people will have seen this movie, but this is the movie about a binary neutron star merger. The gravitational waves are bringing this two binaries, the binary closer and closer. So the emission of gravitational waves bring it closer, and then you have a whole heap of astrophysics that happens. And I mean, that happens on a very quick time scale in terms of a movie, but also in real life as well. But what we can actually see, is of course the gravitational wave observations. I'll just pause the movie there and turn back to the paper.
Sure. Great.
Is we see basically the gravitational wave emission, LIGO sees can detect this gravitational wave emission, which is the ripple in the fabric of space-time when the two neutron stars are coming closer and closer together and, a whole burst of energy goes out. And LIGO can detect these little tiny ripples out to, cosmological distances. So in 2017, we had this amazing discovery of GW 170817, which had the gravitational wave observation.
Mm.
And then we also saw the light that this gravitational wave merger had produced in a whole heap of other electromagnetic bands.
Yes.
So in particular, one of the electromagnetic counterparts we saw was dubbed AT2017 GFO,
Huh?
which is the kilonova that was associated with this binary neutron star merger.
Yes.
So the amazing thing about AT2017 GFO was that this was an observation of a kilonova. Now, if you're not too familiar with what a kilonova is, it is essentially our process nucleosynthesis powered transient. So it's very analogous to what a supernova is, which is the collapse of a massive star, and it's powered by nickel radioactive decay of nickel 56.
Hmm.
But kilonova, on the other hand, is essentially it's a smaller cousin of a supernova in some sense, where it's powered by radioactive decay of our process elements, so elements way down the periodic table on
Right.
your observation on your periodic table of elements.
Uh-huh.
So the amazing thing about 170817 was that we've got this gravitational wave observation on one hand, this kilonova observation on one hand, and we want to link them together. And this was really all, about the field. This is really what started off, in some ways, the field of gravitational wave multi-messenger astronomy.
Well,
Because if you can link what the kilonova is telling us and what the gravitational wave observation is telling us, then you have some sense of understanding things like what powers, what produces the chemical elements, all of the elements in the universe, other things like, how do jets get launched and all these
oh yeah.
different things,
Oh yeah.
properties of what are the properties of the different ejecta, et cetera, et cetera. So,
Cool.
really rich questions in astrophysics. But to actually really answer that, what you want to do is you want to take the observation
Yes.
and you want to, understand what it is made up of in some sense.
Uh-huh.
So I'm going to switch to figure 4 at the end just
Sure.
to sort
Sure.
of
Absolutely.
illustrate the point a little bit.
Absolutely. Figure 4. Bang, bang. So what do we have here?
So I'll go through the rest of the figures in more detail later on, but I just want to
Mhm.
illustrate the point that what you want to work out from, for example, a kilonova observation and this gravitational wave observation is, all right, what is the properties of the binary that made this particular signal,
Okay.
right? You want to understand, well, if I have this kilonova observation, how much mass was there in total that produced this much process elements? What is the quantity of gold, platinum, nickel, etc., that I actually made in this merger?
Okay.
So one of the things you want to do is in a plot like this, which is I'll focus on the blue violins at first, is you have these properties of the kilonova, such as the masses and the velocities, and you want to accurately constrain these parameters so
Okay.
that you can work out what is the elements that are synthesized essentially.
Mm-hmm.
And now I want to switch back all the way to the beginning.
Sure.
To do this, you have to have a really good understanding of what kilonova should look like in the first place.
Okay. Yeah, that helps.
And this is essentially where the problem lies, and this is what this paper was trying to address. In essentially that one of the ingredients that you have in these kilonova light curves. So if you go all the way to the beginning,
Uh-huh.
um, one of the main ingredients.
I'll get there. Sorry.
All right.
Okay.
One of the main ingredients that you have to worry about is this thing called the heating rate.
Right.
So now the heating rate is essentially a very simple thing to, it's just a fancy way of saying how much energy does 1 gram of our process element, our process material produce per
Yes.
second.
Yes.
What is the energetics of, that our process element? So it's
Mhm.
a, very simple thing to work out, but, it's actually a really hard thing to actually know in practice. And as you can imagine, it depends exactly on what elements that are actually produced. So,
Yes.
what amount of energy nickel produces is different from what amount of energy platinum produces. And so
Mhm.
you need to know exactly what quantity of each thing is produced. But then it also turns out that it's also dependent on what the product of that reaction is. So let's just make the analogy back to supernova again, just for a
Okay.
second, because it's easy to
Okay.
think about. When you
Mhm.
have supernovas, you have nickel, some amount of nickel, and it's gonna decay into iron.
Yes.
So you have one sort of decay product you have to worry about, decay chain that you have to worry about. And so you can do a laboratory experiment to try and understand how much energy this nickel, 1 gram of nickel produces, or something like that.
Okay. I'm
Well,
with you.
still might be difficult and hard to do, but it's relatively easy to at least try to tackle.
And it's only one.
And it's only one.
And it's only
Exactly.
one.
Whereas in Kilonovae, you have a whole heap of R process elements. You don't know which ones. You
Hmm.
would love to know which ones because you would exactly like to know which R process elements are produced precisely. In fact, from observations of 1708-17, when we looked at the spectrum, people said, okay, this one particular line points towards strontium.
Okay. Yes.
So we could say that there's strontium being produced in this merger. And then there was another set of lines which people argued could be yttrium, but
Okay.
then some other people argued was actually helium.
Okay.
So there's a
Oops.
whole heap of sort of problems going on. And okay, which elements are actually produced? Which elements do I actually have to care about when I'm trying to calculate this heating rate, essentially?
Hmm. Hmm. Hmm.
So essentially, what goes on into this calculation is trying to understand from a nuclear network, they will look at, all right, if this is my, if this is my, what would I describe it as? If this is my population of isotopes that is produced on the periodic table,
Uh-huh.
on average, I should expect this amount of energy.
Yes.
So this equation one written down here is a parameterization that Oleg Korkabin had written down in 2012, which was based off a nuclear network, which
Yeah.
was saying that this Q dot is essentially the heating rate.
Yes.
So as a function of time, it goes at this particular parameterization.
Okay.
And this parameterization was a fit to a whole series of numerical simulations, essentially.
Nice.
And in
Nice.
fact, so Oleg was the first author. I think the second author was, in fact, Stefan Roswag.
Okay.
So the co-author on this publication
Makes
was
sense.
also on the paper. So this prescription is written down, and a lot of people, especially for 1708-17, use this prescription to build all the ingredients. So
Uh,
essentially what happens when you want to build a kilonova model up is you start with this heating rate. So this is the raw amount of energy that is produced. Then you have to turn to equation
okay.
equation three,
Equation three. Go to equation three, which is down here. Yes. Hmm.
which is what fraction of that energy is actually thermalized.
Yes. Right. Because some of
So, actually gets into light as opposed to just being escaped. So, for example,
yes.
if you have radioactive decay, some of the natural products you might expect are neutrinos and gamma rays.
Yes.
And so neutrinos are just going to go through the ejector without doing anything at all. Neutrino, the optical depth to neutrinos is nothing, very small. So you have to take into account how much energy is lost from the raw ingredient input heating rate
Yes.
because it's not being captured by the ejector because it's just gone through the ejector.
Yep.
So this was another parameterization that Jennifer Barnes and Dan Kaysen did in 2016, which
Hmm.
was saying essentially this is the other ingredient that goes into making a kilonova model, which is given a particular heating rate,
Yes.
how much energy is actually transferred to the ejector,
Yes.
thermalized.
I'm with you. Hmm.
So in 2017, when these observations happened, people were really interested in using these models to try and work out, all right, this is how much ejecta is produced. This is the quantity of this number of this element or, bulk properties because getting a particular element is quite difficult. So at bulk, people were saying that 1708-17 produced about 0.05 solar masses of nickel. I keep saying nickel because I keep thinking of supernovae all the time.
Our process.
But of our process, a material was produced in 1708-17.
There we go.
All right, which is great because then we can
Cool.
use that number to try and understand things like the equation of state,
Ooh,
things like
right.
can GW 1708-17 and binary neutron star mergers explain all the R process elements in the universe and things like that. So a really interesting question.
Indeed.
But the problem is that if you go back to equation one again,
Uh-huh. Sure.
this equation was essentially built on, it came about in 2012 when we were doing numerical simulations, assuming, you know, not assuming GR. We weren't really handling neutrino transport that well.
Okay.
So there were some, missing pieces to the puzzle. So what ends up happening is that um, essentially this this parameterized equation was on built on a foundation that was kind of missing the whole parameter space for
Okay.
Kilonovae.
Yes. Okay.
So in particular, it was only valid for a really, really tiny regime
Oh.
of what Kilonovae could be actually, observed with.
Mm-hmm.
And therein essentially lied the problem, where the model was built on this ingredient and being used in a regime where the ingredient itself is probably not valid.
Out of
And
range.
so there's been a whole bunch of new prescriptions. So Stefan Roswag and Oleg Korkevin. So you can notice that it's quite often the same two teams, and just mixing up the order.
All good.
They actually did a new series of numerical simulations which could capture the conditions of kilonova a lot better. The diversity you might have in initial conditions of the kilonova,
For
and
example,
in
right. Yeah,
particular
trajectory.
the
Mm-hmm.
pro the properties you have to worry about are basically the population of isotopes that you have in the system
Uh-huh.
and at what velocity they're traveling at.
Okay.
So essentially, those two properties seem to matter. And so they came up with this new prescription that is written down in equation two,
Okay.
which is, you can see it's written down in a very similar way, but
Right.
essentially, as equation one is, but essentially it now becomes a function of this property called the electron fraction
Mm-hmm.
and the velocity of the ejector.
Okay.
So now I've produced electron fraction, but I just want to make sure people are on the same page of what it means. The electron fraction is basically a way we have to parameterize how much protons and neutrons there are in total in the ejector itself.
Okay.
It's got nothing to do in a sense with the electrons because those are not really important. So it's actually written down as the number of protons over the number of neutrons. Sorry, it's written down as the number of neutrons over the number of neutrons plus protons.
Okay.
So you can imagine that if you have low electron fractions, then you're low on the periodic table. Whereas if you have high electron fractions, you're sort of more high up,
Right.
essentially.
So low IUs are neutron rich.
Yep.
Yes.
Yep.
Okay.
Perfect.
I'm with you.
So awesome. So essentially, then this function, which is, it's not pretty to look at, but it really well accurately describes, manages to fit numerical simulations that capturing the diversity we get from Kilonovae, and then you can parameterize essentially how much energy is produced by 1 gram of R process
Right.
elements.
Very cool.
And it is a function of this electron fraction and the velocity of the ejector.
Yes. Okay. Okay.
So why we wrote this paper as, saying it's a cautionary tale is essentially to point out that if you just change this one little ingredient, you can completely change what kilonovas look like for the same input parameters.
Okay. Okay.
So now I want to turn to figure one.
Okay. I'm with you. I'm with you, my hero. Boop, 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 boop. And figure one. Here we go. Light curves. I need to do a little light curves.
So what this is showing is the magnitude at 40 megaparsec. The 40 megaparsec is motivated by observations of 170817 that happened at
Mhm.
about 40 megaparsecs.
Yeah.
And then it's showing in different filters, so different wavelengths for the observations. And because we wanted to look towards the future a little bit, we chose LSST
Good.
as an upcoming survey that is going to be, amazing for finding transients in general, hopefully, and particularly to follow up other gravitational wave events. And
Mhm.
so what I'm showing here is three different random kilonova parameters. So I'll focus first on the red curves,
Okay.
where the prescription, there is only one difference between the model, essentially, the kilonova light curve, the dotted curve, and the solid curve.
Uh-huh.
The only difference is the heating rate that we choose as the input.
Okay, I'm with
So
you.
either we choose equation 1 as an input, or we choose equation 2.
Correct. I'm with you.
And so you can sort of start to see that there's a massive difference
Yes.
in certain parts of the parameter space and then
Hmm.
slightly little in others
Yeah.
on what the kilonova looks like, where the only thing you're changing is this prescription for the heating rate.
Yep. How much energy you
And
inject?
so if that is, if that is a problem, then if you look back at 170817,
Yes.
most of our observational inferences, so the observations of 170817, 802017 GFO,
Hmm.
were in the constraints we made were by the prescription, which was set by this dashed curve instead of the solid curve.
Okay. Okay. Uh-huh. Uh-huh.
So if there's such a big difference by just the prescription, then you can imagine that all the parameters we inferred, could
Will.
also be wrong.
Right.
And we want to try and understand the size of that bias so that we can, actually robustly try to answer, all right, how much ejecta there truly was, what are the properties of it, and then how it relates to different questions.
Cool.
So I just want to also highlight another fact, which is the difference is different in different parts of the parameter space. So the red curve is, a region which is showing a massive difference, whereas the green and blue curves
Right.
are not so. So the difference in the dash and solid curve and the green and blue, which is just different kilonova parameters, is not as severe. And
Yes.
that's essentially because in other parts of the parameter space, the kilonova heating rate that the new input gives starts to resemble the old one because the old one was still right in
In
that
that
part of
regime.
the parameter
Okay.
space that it
Okay.
is.
Okay.
And so this is just, in a way, a sort of nice self-consistency, but in a
Yeah.
way, it's saying that if we happen to have an observation where, with probing parameters that are green and blue, the difference due to the heating rate is not as bad. So,
Right.
we don't have to worry about it as much.
Mm.
If you think about what the observational uncertainty might be, then,
Hmm.
it could just be within the observational uncertainty.
Okay.
So those were sort of three representative cases where we could make an individual light curve. One of the interesting things to also think about, and if you turn to figure 2,
Yes. Okay, 3 bands, and now we do credibility intervals.
so what this is showing you is the same sort of magnitude at 40 megaparsec in the same filters, but now instead of just drawing three different light curves,
Ah,
we're drawing 5,000 randomly from what we think the prior distribution of kilonovae might look like.
okay, I'm
We
with you.
don't know that very well, but we have some, guesses of what that might be. And we want to broadly show what the difference in prescription causes on the light curve.
Yes.
So here, the blue is the kilonovas that would be produced. So it's basically a shaded interval of all the regions that the kilonova could cover. So the way to interpret this plot would be
Okay.
that at 2 days, if you follow the blue prescription, the kilonova light curve could be from 27 mag to 21 mag. So it's a huge
Yeah.
range.
Yeah.
But the important thing is the phenomenology. So the blue is the old prescription
Okay.
and the green is the new prescription.
The
And
dark
the
green or the
key
light
thing
green?
to notice,
On
sorry,
on the green, do you mean the light? green or the dark green or
Yes, yeah, that light green, yeah.
light green? Okay.
So because it's basically shaded it on top, yeah.
Right, right.
Um,
Okay.
so this light green region is
Uh,
in the new prescription, and the dark blue is the old prescription.
okay.
And so the key thing to notice is that on average, the kilonovas that are produced by this new prescription are dimmer.
Mm-hmm. Mm-hmm.
So, if we have a chance to observe them, we have to look deeper to find the same kilonova
Yes.
because, they're going to be dimmer intrinsically.
Right.
And importantly, they have much more breadth in their decline rates.
Ah, yes. Okay.
So
Really?
the important thing with Kilonovae is that the decline rate actually really accurately tracks the heating rate.
Yes.
And so in the old prescription, the heating rate was essentially always the same, no matter what the properties of the kilonova actually were,
Okay.
because it was just essentially just trained on, it was a uniform sort of universal heating rate.
Right, right,
But
right.
because the
That's for
heating rate
somewhere.
now actually depends on the parameters of the kilonova,
Right.
the shapes that you can get out in terms of decline rates essentially are very different and they depend on the parameters themselves.
Good. Good.
So, and that is one of the sort of key points in this, one of the sort of key
Cautionary
minor
tales.
points in this paper. Sorry,
Cautionary tales.
cautionary tales, in that uh, Kilonovae are not, always going to look exactly the same as they did for 1708-17. They'll fall off in exactly the same way. They could have a wide weight of intrinsic diversity just purely based on the heating rates.
Right.
And I'll get to all the other ingredients later, which is an even more of a cautionary tale in some sense.
Okay. Okay.
So that was one of the main results, just showing sort of, that there's a massive difference in the light curves. But then one of the main questions we wanted to ask is, all right, if I have observations, such as I did for 1708-17,
Yeah.
where I actually interpret the observations with the old prescription,
Okay.
how different would my results be if I use the newer set of models?
Yes.
Everything is the same. It's just that I've changed this heating rate input.
Good up. Mhm.
And we wanted to steer clear from 1708-17 in a way because we didn't know the true input there. So the way we decided to tackle this was we looked at some synthetic examples where we could actually say what is the true input itself.
Yes. Recovery.
So where we know the ground truth so that we can, test whether everything is sort of correct and we can say things and
Out.
whether we're accurately recovering things.
Correct.
So
Yes.
what I want to go down to figure 3 and just sort of highlight a key point.
Okay. Figure 3.
Right.
Okay.
So the way we went about this was, now we're looking at flux density, which is another way we can, say how bright the thing is.
Mm-hmm.
And now this is a simulated observation of what a kilonova would look like in LSST if it's followed up by LSST in following a gravitational wave merger.
Okay.
So I'm simulating it, so I know exactly what I put in.
Yes.
And I should be able to recover exactly the same things. And that's the key point.
Yes. Yes.
But what I also want to highlight is when we actually go around fitting it, and we don't know what the ground truth, if we just look at it by eye, we might not be able to tell the difference.
Yeah. Right.
So on the left-hand side, it's the same observations, but I have deliberately fitted with the wrong prescription that I put in. So not the prescription that I actually generated the data with.
I'm with you.
And on the right-hand side, it's the correct input.
Okay.
So misspecified input on the left side, correct input on the right side.
Got it.
And the point is that if I just told someone to, look at the fit and say which one is the better fit, there's no way to tell.
They're right.
They both look pretty good.
Yeah.
They seem to match the observations well. And
So
if they don't, you might not worry about the input heating rate. You might think about, oh, maybe there's some other physics going on.
Right.
And this is another key problem when we cautionary tale about 1708-17. One of the big puzzles about 1708-17 was that this early blue part of the kilonova
Yes.
seems to be moving really fast.
Yes.
And the speed at which it's moving is inferred by these sort of inferences on the fits to the light curve.
Ooh. Okay. Ooh, ooh,
And
ooh,
so is that fitting based on a correct
ooh.
ingredient? Is it
No.
actually pointing towards missing physics, or is it just inputs that are wrong or uncertainties that we didn't sort of take into account?
Uh-huh.
People, in fact, added other physics. So 1708-17's early part, people seem to think that it might be because of the hypermassive neutron star that is formed in the merger. So this neutron star immediately after the merger sort of makes the ejector more blue and more energetic, or it could be that it's ejector interacting with the relativistic jet.
Bang.
And
Right.
so there's all these sort of other ingredients, and you could really just ask the question, well, what if we've just inferred the parameters wrong
Fair question.
because we had the wrong input heating rate?
Right.
So
Right.
that was sort of, just an exercise. And when we know the truth, and we just change the input, we could still get it wrong. So turning to figure 4,
Right. I'm with you. Okay. Back to figure 4, what we started with.
back to figure 4. So when we want to ultimately understand the properties of the ejector velocity, the masses, etc., I've got the blue violins there, which is when I fit, I can get a distribution of what the properties are.
Uh-huh.
So the crosses are where I know the true input is because
Okay.
I simulated it, so I know what the true input is.
Put it in. Uh-huh. I'm with you.
But the orange violins are essentially what would have happened if I would have not fit with the correct input
Okay.
prescription. I would use the old prescription.
Right. Mm-hmm.
So this sort of illustrates how big a difference it can cause.
Quite.
Essentially, where the
Especially.
ejector masses would be completely missing the input. So your posterior, the distribution that you infer,
Yes.
would be completely inconsistent with the crosses.
Yes.
So let's say you inferred 0.05 solar masses of ejector, the
Yep.
actual answer might be at 0.01, and you
Okay.
just completely ruled it out.
Right. Hmm.
And then the velocities as well, you can see it more clearly where the value, the orange posterior, that violin is completely inconsistent with the blue violin, which is where the true input is.
And always
And
shifted toward higher velocities and lower masses, right?
sorry, could you ask that question again?
So on the orange one, it's always shifted to higher velocities and lower masses.
Yeah, and that's actually a product of essentially the heating rate. It's a good
Oh yeah,
question.
yeah, yeah.
Because it's essentially has to compensate for the overall energetics by, you
Yeah.
think about mass half mv squared, it has to sort of essentially compensate for it in some ways
Yes.
because the velocity is going that way in another one.
Yeah, yeah.
The other thing to notice is that the velocity posterior, so how much we constrain the velocity by, gets a lot tighter
Yes.
when we have the new input heating rate. And
Mhm.
that's because the shape of the light curve is actually a function of the velocity.
Yes.
And
Okay.
so if you constrain the velocity, if you constrain the shape of the light curve relatively well, then you actually get an independent handle on what the velocity must be as well, which is not true of the old prescription because the old prescription
Yes.
says that it always declines with this velocity no
That
matter
was
what,
independent of that. Uh-huh.
no matter what velocity it is.
Right. With you. Uh-huh. Cool.
Now, this is a very optimistic view of the problem in some sense, because in
Okay.
reality, and if you have ever done nuclear physics sort of calculations or uh, any calculations with supernovae or kilonovae or any type of transients, even the updated prescription we have, equation 2, is still probably not the ground truth.
Right.
because there's still underlying uncertainties in the nuclear physics.
Successive approximations. How about that?
Exactly, exactly. So one of the sort of last parts we wanted to highlight in this paper is what actually happens, how well is your systematic uncertainty on all of these parameters, given that even with the new prescription, there
Mm.
is still an uncertainty on that rate itself,
Yep.
on the heat rate.
Yep.
You know, the new heating rate, for example, says that 1 gram of our process elements produced 10 times 10 to the 18 ergs per second
Okay.
per gram.
Reasonable number. Yep.
Reasonable number. But then in reality, if you use someone else's nuclear code, you might get 50 times 10 to the 18.
Okay.
You might get 10 to the 17. And
Yikes.
so
Yikes.
so we wanted to sort of see, given what people have predicted for the overall uncertainty on this heating rate,
Hmm.
what does that translate into in terms of a minimum width on these posteriors that is just a function of the fact that we don't know the uncertainty on the heating rate well enough.
Okay, cool. I'm with you.
So just to say it another way, because we don't know the heating rate precisely and itself has a heating rate uncertainty,
Yes.
what is the minimum size on the uncertainty on all of these parameters just because we don't know that one ingredient well enough?
Yes. Uh-huh.
Awesome. So that was essentially what the last part of the paper was. And one of the figures that I'll turn to just to...
Okay.
Oh, no, that's the full figures. I
That
completely
was four.
forgot.
We don't have another one. There's only
That was-
four in this. I missed one.
But that was essentially, so it didn't come with a figure, but essentially what you can do is you can look at what the difference in heating rate will be if you have different mass formulae, nuclear mass formulae.
Oh, right. Sure. Sure. Hmm.
And so essentially, you know, how much of the periodic table you go and what isotopes are produced are, you know, these are written down by these nuclear mass formulae in some way, some sense.
Right. Right.
And there's a lot of two different models that exist that are popular in Kilonovae field.
Uh-huh.
One is from this Duflo-Zucker
Yep.
model, and then another is this finite droplet
Yep.
mass form.
Hmm.
And they actually, and people have sort of shown this
Right.
before, and you can see the people who have shown this before, Jennifer Barnes and Stefan Roswog, that they produce up to an order of magnitude difference in the heating rate.
Yes. Hmm.
So essentially, then we played this game of,
Right.
again, if we have synthetic observations where we know the true input,
Right.
how well should we be able to constrain everything, given that there is an order of magnitude uncertainty on just the heating rate?
And just the basic nuclear physics, right? What's the mass of these things?
Exactly. And so as we were doing this, it was quite evident to us that this is not actually the only ingredient from nuclear physics that goes into Kilonovae modeling that has a lot of uncertainty in it. There's this thermalization fraction, so that equation
Yes.
3 that I showed.
Uh-huh.
That is also very dependent on how you choose to parameterize things and
Uh-huh.
what the actual nuclear species are and what velocities and stuff they're traveling with. So
Yes.
that people have independently studied to say that there's an order of magnitude uncertainty on that
Okay.
alone. So the punchline was that at the end of the day, if you combine all of these uncertainties, then at best, until we resolve these uncertainties, your properties can be only inferred to within an order of magnitude. Your
Fair enough.
properties such as the velocity,
Mhm.
masses of the kilonova
Right.
are limited to about an order of magnitude.
Yeah.
And it's worse in certain parts of the parameter space. So if it's lanthanide rich, so if it's a low electron fraction,
Right.
then the uncertainties are bigger.
Yes.
And so the numbers will be larger. Whereas if it's lanthanide poor and the kilonova appears more bluer, then the uncertainties are smaller, but still there's a sizable uncertainty.
Yeah. And there's
And
also,
essentially what we provided was that this is this cautionary tale into what the underlying ingredients are. And this is one way you can actually try to quantify how much this uncertainty would be by
Right.
doing this sort of end-to-end analysis of simulating an observation where you know the input and trying to understand. And we made this sort of software package in a different paper where we essentially sort of provided this whole workflow. So this package is sort of highlighted and read back right
Right
there,
back.
which
There
is
we go.
essentially making this possible for us to study this sort of uh, whole procedure in a good detail.
Well, I'm a
And
big
that's
open.
basically what this paper is about.
Very cool.
Cautionary meeting rates.
Very cool. Very nice. Beautiful. Beautiful, beautiful. And I'm a big fan of open source software, so there's a good kick for Redback. Very
Awesome.
beautiful. Nikhil, thank you so much for walking us through your awesome APJ letter.
No problem. Thank you. Thank you so much for having me.
Let's see. And you kind of touched on it a little bit, and it's always just kind of fun. So where do you think we go from here, given the published article? One can always hope that we will find another 10 of these systems, and that's a hope. But hopefully at least one more would be interesting. But where do you think we go from here, given the published article? How do we resolve some of these difficulties?
So I think that's a great question and something that I've been thinking quite a lot about. One of the things that is this paper comes as a series of papers in a sense, and not just from me, but from other people in this community,
Mhm.
where people have looked at, essentially the cautionary tales, but for different ingredients of this overall Kilonova modeling puzzle. So there was a recent paper that was essentially pointing out what is the uncertainties because of the atomic calculation. So
Opacity.
what sorry?
Opacity.
Exactly. So opacity, where, what is, this element's line list
Right.
and
Mm,
how much does it radiate in this color and this color and like that color, that sort of thing, how much does it absorb because of
right.
essentially what is the elements made of. And
Yeah.
this is quite important in a different way because when you want to have the discussion about looking at the spectrum and trying to identify what particular element it is, you want to know this line corresponds to this element. And you
Yes.
want to know that pretty robustly. So that's been something that people have sort of taken forward. And that's quite interesting because we recently had these long GRBs,
Oh,
which
yeah.
have a kilo in them. And so this is a really interesting sort of puzzle now in this field where short GRBs should be coming from binary neutron star mergers. And this is what 170817 showed, and we believed this for a very long time.
Uh-huh.
Uh, and they are also accompanied by Kilonovae, so everybody's really
Yay.
happy.
Yeah.
But then these long GRBs now, so 211211A and
For example.
230307,
Yeah.
the numbers just stay in my mind.
You do that.
Numbers
You
are
do
not
that quite
important to
well.
remember.
You do that quite well.
But essentially, there's these long GRBs that appear to have a kilonova
Yeah.
for some reason. And in particular, for the latter GRB, 230307, we
Mhm.
actually had JWST observations of the spectrum. And so it was amazing observations which showed the near infrared spectrum of this long GRB.
Yes.
And if you overlay the spectrum of 170817 on top of this,
Okay.
of this GRB spectrum,
Okay.
you essentially have a feature at 2.1 micron that
Okay.
is present in both of these systems. So really exciting because whatever this element is,
I
or
was going
whatever
to
this
say.
corresponds to,
So what is the element?
we think it's tellurium,
Ooh. Ooh. Ooh.
but we're not sure entirely because this is as you're aware, this is a really hard problem to solve.
Yeah.
And so many, and when you get to our process elements, unlike hydrogen, for example,
Yeah.
there's just so many transitions you have to worry about. So it
Correct.
becomes quite hard. But for whatever reason, this GRB, which is about 100 times longer than 170817's GRB,
Yeah.
has ended up making a kilonova that looks quite similar and made the same feature, hopefully same element itself.
Yep.
So I think it's a
Cool.
really interesting puzzle right now, and I think that's sort of the future direction to try and nail down, what properties are linked together and what that ejector is actually, and what are the properties of these two different systems, so that we can work out what is the underlying diversity. And at the same time, we can always work towards improving the nuclear calculations, because
That's awesome.
once we know this is the element that we need to care about,
Yeah.
we can tell the laboratory
Fair
people,
enough.
all right, just focus on this element only,
Yes. That's a lot
pin this
easier
one
than,
down first.
no, cover the whole, our process plan. Okay, well, that's
Exactly.
a little difficult.
So So it's this, I think, really nice interplay in this field right now for basically observations guiding theory. I would say neither of them are far enough along that they could completely, explain the story. So
Right.
it's very, very different to,
Okay.
I would say, supernova 1As, where the empirical model is used by cosmologists to do really
Ah, ah,
precise things,
ah,
but
ah.
we don't actually understand
Right.
how a supernova explodes that
Scan
well.
angle and all. Right. Mm-hmm. Mm-hmm.
So whereas I think Kilonovae is in this fun game where the models are, developing, the observations are coming, and I think who knows who's gonna inform what, and
Yeah.
maybe it's just the back and forth.
Yeah, well, that's the usual case, right? So
That's the
back and
usual.
forth. But very cool. It'd be really exciting to see this develop over the next couple of years, particularly with Vera Rubin coming online, the observatory coming online, and the advancement. And there's a lot of action in the nuclear physics community on this as well, because it's providing a motivation to do this. So it would be really exciting to see these fields um, come together over the next couple of years, or start to converge on where we're going. So, and I will always keep my fingers crossed for another 2 or 3 observations of actual Kilonovae at 40 megaparsec.
Oh, that would be incredible. Yeah.
That would be great.
Yeah.
Cool.
Another actually, just to point out, because you sparked that point in my head, I think the upcoming sort of instruments circa 2027 or so,
Hmm.
that are going to target things in UV,
Ooh, yeah. Hmm.
that
Mm.
will be particularly distinguishing for models as well.
Get them
So
early. Get them early,
there's an
right? Yeah.
exciting time.
Prompt. Very cool.
Yeah.
Nikhil, thank you so much for walking us through your very
Thank
lovely.
you.
Cool. And that will do, everyone. And I hope this made your astronomy day just a little bit better. We will see you on the next one. Bye bye.